You by now should know what that sound means. We've got another great speaker coming up onto the stage. This next talk is going to be meta settlement. Sorry, it's not that. It's decentralized memory for the world computer. It's a new paradigm for Web3. It's being given by the co-founder and CEO of Optimum, Muriel Médard. Please give it up for Muriel.
Thanks, Daniel. Yes. So let me see. Great. So it's a pleasure to be here today. I'm Muriel Médard. I'm going to talk about decentralized memory for the world computer. And I hope to convince you that this is a correct way of going about things, and also is going to be the most efficient and future-proof way to go about things. I'm just going to tell you a little bit who I am. So I'm on leave to pursue this full-time from MIT. At MIT, I was holding the NEC chair for software science and engineering for the entire School of Engineering, and full professor in electrical engineering and computer science. I'm an MIT product, have 3 bachelor's degrees and so on. And, you know, things were going so well in academia. You know, I was getting all the nice kudos. And it was really something where leaving and coming to do this full-time was a huge jump. And I hope to convince you, as part of this talk, that I made the right jump, because I really believe that. So let me step back and talk a little bit about when I made that jump. So this is technology that has been coming out of my lab. I've been working on for almost 2 decades, you know, slowly building it up. And so, you know, what were we thinking when we started building this technology? Well, we were starting to think about things from really the ground up. You know, that's generally how we try to approach things. And building things from the ground up means to say, well, what does it mean to? And let's start with, what does it mean to be a computer? And in particular, what does it mean to be a decentralized computer like Web3? So, you know, here's the Web3 stack that we know and love. You can argue as to whether you might, you know, compact some of these layers, add some layers, but, you know, I think we can, most of us agree on these types of layers. And I'm going to group these layers in sort of the top layers and the bottom layers here shown in purple, with the actual hardware shown in white. And I'm going to try to map this to what a computer is, starting from scratch. I'm going to try to map it to the von Neumann architecture. So, you know, it's after World War II. People are really starting to think about what does it mean to have a computer. You know, we've all heard of Turing and, you know, breaking the Enigma machine and so on. And so, you know, there had been a lot of thought about what a computer is. And von Neumann basically said, okay, here's what is a computer. Well, you have to have an input and an output, right? You have to have compute over something, and you need to then spit out the answer. We're in agreement. And then what goes inside? Well, you have the central processing unit, you know, our beloved CPU, which has control arithmetic. And then you have to have the memory. And you also need to have a means of getting to and from the memory. So when you compute, you write to memory, you read from memory, back and forth. And if we look at Web3 and we say, you know, how does that look? How does this look relative to what something that von Neumann would recognize? It doesn't look too weird. Okay, maybe locally weird, but overall you're like, yeah, you know, you have operating systems, EVM, SVM, you can argue to what extent they're applications or not, and then people build on top of those, you have applications. So it looks fairly recognizable. When you go down here, it doesn't look like that at all. It looks really, really different from the way your computer works. So if you think of memory as being a closet, and random access memory as being a closet where you put and take things out and are able to find them easily, We don't have things that look like that at all. So, for instance, let's look at the bus. We use gossip, which is really slow. And anybody who's bought a computer or had to build a computer and put in a bus, you know that if your bus is too slow, that's going to become your bottleneck. If you look at what's happening in the memory, it doesn't look like a closet where you put in things and take things out. You have the mempool, which looks like a pile of laundry on the floor, and you have to rummage through it to see what's in it. You have full nodes, which is a closet that has everything you've ever had, starting with like your baby onesie. And then it looks so scary in that closet that you don't even want to go in there and look, so you pay somebody, maybe DA, to go and tell you whether, the jacket that you're trying to wear is there. So that doesn't look at all down here like what we would have in a normal computer. And our thesis is the following. If you're going to do something really different from von Neumann, sure, go ahead and do it. But you better give me a really, really, really good reason as to why. And why is that? Well, it would be one thing if we said, well, look, I realize I'm doing things a funny way, but hey, I'm happy and everything's cheap and great. No problem. But, it's not cheap and great. Things are slow. Transactions are slow. Storage is slow. And scaling becomes really, really difficult. And of course, one of the core aspects of decentralization is that it should be what allows you to scale. So if somehow scaling is becoming a challenge while decentralized, then that's not what we were trying to do. So the approach that we're suggesting is let's go ahead and have a decentralized computer that looks like a dedicated computer. And if you think of other decentralized networks that have really scaled and sort of been able to take the test of time, stood the test of time, that's how they work. They're decentralized, say, the electric grid is decentralized, but I have a socket. And that's how I have something which it's an abstraction, which happens to be it looks like a battery, and it works just fine. If I go to Web 2, I also have something that's decentralized, and I have a socket. The socket is a web socket, and it makes it look like I have a point-to-point connection to somebody else. So what am I going to do here in Web 3, I need something that's decentralized and is going to work like dedicated bus, dedicated memory, but I need that to work in a decentralized way. And I need to have the correct APIs, right? A socket is just an API, and so I need an API to a completely distributed system. Okay, so how do we do that on the memory bus? So I have things that I'm trying to propagate. Say I'm trying to propagate blocks. And we know how gossip works. You send these blocks around, and you hope that people get it eventually. And it's slow. Why is it slow? The physical links aren't slow. So something's slow. It must be that the protocol is slow. So imagine that I'm trying to propagate these pieces, and I'm trying to reconstruct all the different pieces. If I'm trying to propagate them one by one and duplicating them, I'm sort of gumming up everything. Versus if I just give you equations which represent the data, the numbers that you're trying to send, then I can reconstruct it from those equations very, very efficiently. So that's basically what we do in our gossip, in our Optimum P2P. We use random linear network coding, which was developed in my lab, of which I'm co-inventor, and we use it in gossip. And it's provably optimum, which is why we call this Optimum. It's provably optimum. Some of you may have seen some of the research papers that came out on the Ethereum Foundation about this, and the huge gains, like 50-fold gains that they see. So basically, this is what we are building with our technology licensed from MIT. Okay, so basically, that gets us to this point here. This API to actually be able to propagate the data. Remember, this is what we need, our bus, in order to get to and from our memory unit. What next? Well, we have the decentralized memory. Now that I can get data around, I'm going to do reads and writes. what do these reads and writes do? So in the 1980s, IBM went ahead and said, let's find out what are the axioms of what a computer memory should be. And let's go back to the closet I talked to you about. You first have to have atomicity. If I'm pulling a dress out of the closet, I don't end up with just one sleeve, okay? I pull the whole dress, either it's there or it's not. Consistency. This is a shared memory. If I put a dress in the closet and then you put in a jacket and somebody comes in afterwards, they may see that neither of us put something in, or only the dress, or the dress and the jacket, but they're never going to see just the jacket. They're never going to see something that was not true. You might see old information, you're never going to see incorrect information, out of order information. And lastly, you need to have durability. If I stick something in the closet, it's going to stay there until I decide that it's not going to stay there anymore. Okay, so I need to have something which is dependable. If I turn on my computer, I expect the stuff that I put in memory is there, and if I want to put it in cold storage, I do that. I decide how to do that. So we are able to do this in terms of reads and writes, multi-reader, multi-writer, and the real trick here is that, there were a couple of algorithms out there in the computer science literature. Those of you in the area may know ABD, Rambo, and but this is a very niche area. But, the reason they stayed fairly niche was because they were doing a lot of duplication, not using coding, not using equations. So the way we're able to make this scalable, fast, reliable, and economically attractive is by using coding. So then what? Who benefits from Optimum? Validators, and then of course L1s and L2s. And let me push particularly for validators, because this is our first go-to-market is on validators. Particularly with our first offering. So of course, first you need to do the bus before you do the memory. We're looking at speeding up block propagation and lowering operational costs. And of course, the feedback we've gotten, the reaction we've gotten from validators has been great. So if you're a validator, if you work with validators, we would absolutely love to chat with you. Down the road, then, of course, when you have the DRAM, you have something that really is going to work on helping you with your MEV, preventing sandwich attacks, remember, because in that closet, everything is always appearing in order. Things never get out of order. You can't fake anything. And of course, for L1s and L2s, the gossip is able to really increase the bandwidth and reduce latency. Whether you were using something like, say, Gossip Sub, particularly in Ethereum, or whether you were, say, working over Solana and working over Turbine, which has like 1950s style coding, making of those equations, which of course we can outperform. And then of course the Optimum DRAM ensures global order is really going to basically ensure correct operation without having to go back and fix things when they go wrong, etc. So this framework here of the atomicity, consistency, durability is often called the ACID framework versus what we usually do in Web3, which is the base, best effort, eventual consistency, and basically, just trying and seeing what happens. So what's our call to action? We're launching, it's March 1st this month, a private testnet and running POCs. It's a private testnet. If you're interested, please come talk to us. Please follow us on X. Very exciting. We announced our angel round yesterday, so follow us on X. You can see it. We have really an amazing set of backers, very supportive, really helpful. Our research papers on decentralized propagation and memory are coming in the coming weeks, so look for them on archive. Feel free also to reach out directly if you'd like a copy of them. And with that, I really hope that you'll try to contact us if you're in the in the business of doing the of running nodes, and I look forward to hearing from a lot of you. Thanks a lot.